Hi, so in the last video we used Gauss's law of electricity to derive the electric field some distance away from an infinitely large plate. And today we're going to be using that to estimate the electric field inside of a parallel plate capacitor. So we can look at a parallel plate capacitor and just see two infinitely large plates. Now you might say, well, the capacitor is not infinite, and that's true. And so, for example, when you get near the edge of a capacitor, you'll end up having some field lines that become non-parallel. And those field lines are called the French field. But we can ignore the French field and get a very good estimation, very good approximation. So we're going to go ahead and do that. So the E field caused by one of these plates is the charge density of the plate divided by 2E0. And as you can see from the positive plate over here, it has a certain amount of E field lines pointing in either direction. And of course, positive points away from, and with negative charged plate, negative charges point towards themselves, the E field does. And you'll notice that if there's 4 lines over here and 4 lines over here, there's actually going to be 8 lines. And so effectively, they're all pointing in the same direction as well. So it looks like in between the two plates, we could say that it's double the electric field as a single plate. And so if we double the electric field, we get 2 sigma over 2 epsilon 0. And that cancels to 1, and so we've proven that the E field inside of a parallel plate capacitor is equal to the charge density divided by the permittivity of free space. Now that we know that, why don't we go ahead and try to prove how to calculate the capacitance of a parallel plate capacitor. So we know that the E field inside of the capacitor is equal to sigma over epsilon 0. And let's take a look at the capacitor from a different angle. Let's look at it from an oblique angle. And one of these plates is positive, the other one's negative. Now the definition of capacitance is charge per volt. So for example, if your capacitor is 1 farad, then that means it can fit 1 coulomb on it per volt that you give it. So if you give it 2 volts, now it'll give you 2 coulombs of charge on the surface. So if we know that, Q over V, that's not really, it doesn't look like it has any spatial dimensions to it. They're all units that don't really have spatial dimension. So we're going to look and see if we can compare those spatial dimensions of the actual capacitor. I'm going to call the distance between the two plates D. I'm going to call it D. And I'm going to call the area of one of the plates, I'm going to call that A. And so let's see if we can write charge in terms of any of these and also voltage. So if you'll recall that half of Faraday's equation says that V equals the line integral of the electric field dotted with some length of line. So E dot dl. And if we look at this from the side, you'll notice that the electric field is pointing this direction. And what if we wanted to be a charge? Let's be a charge that starts on this side and works its way over this way. And so what that would mean is that dl would be a small line segment along that path. Well, we can write E dot dl as E times L times cosine theta. The reason being is because, well, let's write it as E dl cosine theta equals voltage. And we know that cosine of 0, because look, the E field and the dl vector are going to point in the same direction. So the angle is 0 between them, which means that cosine of 0 is 1. Now the electric field is roughly constant inside of the parallel plates, so it doesn't matter where you're at, E will be the same. Therefore, E is constant with respect to dl. So we can pull E out and integrate dl, and what we'll end up with is we'll end up with voltage equals E times L. And what I was calling L here looks like, on our schematic here, it looks like D. And so we could say that voltage equals E times D. All right. So now, how could we write charge in terms of spatial dimensions? Well, first let's take E times D and rewrite that, because we know that E in a parallel plate capacitor is sigma over E0. So that means that voltage is equal to charge density times the distance between the plates divided by the permittivity of free space. And now for charge. So if we were to write this, we could say that C, capacitance, now equals charge divided by sigma times D over E sub naught. Okay. Now we know that charge density, sigma, charge area density, sigma, can be written as the charge, or the Q's, per unit area. Likewise, we can multiply area over and say A sigma equals Q. I can now replace Q in this equation with A sigma, and thus I will get C equals A sigma divided by, and I'm going to invert and multiply this, A sigma multiplied by E0 over sigma D. So the sigmas cancel, and what you end up with is that capacitance of a parallel plate capacitor is equal to the area of the plate times the permittivity of free space divided by the distance between them. And this is the full story for any capacitor that's air-filled or that is vacuum-filled. But it's important to realize that different materials can be put between the plates, called dielectrics. And those dielectrics will have different permittivities than necessarily just free space. And so in order to account for that, we put a constant times epsilon 0, and that constant, K, is known as the dielectric constant. And for different materials, you'll have a different dielectric constant. It will always be, K will always be greater than or equal to 1. For example, in free space, K is equal to 1, whereas for maybe different forms of plastics or materials, you're going to have a K that's larger than 1. Alright, I hope this video about using part of Faraday's law to prove capacitance in a parallel plate capacitor is useful, and see you in the next video.